And so we're very glad to have Nathanael Arkor here today from the University of Cambridge, who will be talking about higher order algebraic theories and relative monads. So you can start when you're ready, Nathanael.
Thanks, Sean, and thanks for inviting me. So I'd like to thank Marcelo Fiori, who's my supervisor, for introducing me to some of the topics I'm going to be talking about today. So today I'm going to be talking about joint work with Dylan McDermott, and the focus is sort of the intersection between Linton's monad theory correspondence and the work of Fiori and Mahmoud on second-order algebraic theories, which I'm going to introduce soon. So just as an outline of the talk, first of all, I'm going to recap what an algebraic theory is, just as a reminder, though I'm sure many of you are familiar with the concept. And then I'm going to introduce second-order algebraic theories, which are a generalization of algebraic theories to operators that are often found in type theories. And I'm going to talk about some questions which naturally arise once you've introduced second-order algebraic theories. But before answering those questions, I'm going to introduce another generalization to higher-order algebraic theories, where we generalize from first order and second order to nth order for arbitrary n. And then I'm going to answer the questions I posed nearer the beginning. So I'm going to give a universal characterization of the category of nth order algebraic theories. And I'm going to talk about a monad's correspondence for higher order algebraic theories. If we have time at the end, I'll also talk about what zeroth order algebraic theories are and some interesting observations to make there. So let's start with algebraic theories. Algebraic theories are a categorical formulation of universal algebra that were introduced by Levier in his thesis. So first of all, I'm just going to recap some examples of first order algebraic structure, so we're all on the same page. So first order operator is the sort of operator you'll find in traditional algebra. So we have things like groups, rings, monoids, etc. So some examples of operators are multiplication operations, which are binary, inverses, which are unary operations, and then we might also have things which are multi-sorted. So at the bottom, I've got an action here where the object A is acted upon, it acts upon the monoid M. So we can represent these algebraic structures, so structures with these kinds of operations, categorically using the notion of algebraic theory or Levier theory. So an algebraic theory is effectively a Cartesian category whose objects are generated from a single object, which it represents the single sort of the theory under finite products. So on the left-hand side here, we have a category which equips the structure of the equational logic of algebra, represented by the free Cartesian category on a point, a single object. And we've got an identity on objects functor to some other Cartesian category, which preserves those finite products and equips the category on the right with the equational logic, essentially, of the algebraic structure. So here I'm using Cartesian to mean having finite products rather than having finite limits. So how can we view these functors, these algebraic theories syntactically? Well, the objects of the category on the right are given by finite powers of the generating object X. And morphisms are going to represent terms. So if we have a morphism from xn to xm, this is going to represent an m tuple of terms, each of which has n variables. And another way to think about this is that our morphisms are n-ary operations. So our morphism here takes n inputs. And these two ways of looking at what the morphisms represent are sort of complementary. Now, a map of algebraic theories is just a commutative triangle, sort of the obvious notion of morphism. And together with algebraic theories, these form a category, which we're calling law after Levier. We're not going to talk much about maps themselves, so you don't really need to worry about this if you're not familiar with them. Now, the category of Levier theories or algebraic theories is very well behaved. In particular, it has small limits and co-limits, and this allows us to combine theories in various ways, which is very useful generally. And actually it has a stronger property than that, in that it is locally strongly finitely presentable. And this means that the category law is freely generated under sifted co-limits on a small co-Cartesian category, so a category with finite coproducts. Now, sifted co-limits are a little bit less well known than some other class of co-limits. And if you're familiar with filtered co-limits, they're analogous to filtered co-limits, in that filtered co-limits are those that commute with finite limits in sets, whereas the sifted co-limits are those that commute with finite products in sets. So they're the appropriate notion of co-limit for algebraic theories where we're talking about finite product structure. So if you've come across the INS completion, the completion under filtered co-limits, the SINS completion is very similar. And I'll just note that if our category C is co-Cartesian, then there's an alternative explicit representation of the sifted co-completion given by Cartesian functors from the opposite of the category into set, which will come up later. Now, the perhaps more interesting fact about algebraic theories is that we have this equivalence between the category of algebraic theories and finitary monads on the category of sets. And this is an observation due to Linton. What is possibly less appreciated is that there's another representation of these monads, which is as the sifted co-continuous or the strongly finitary monads on set. And these are the ones that preserve sifted co-limits rather than filtered co-limits. And these two classes coincide for set. So while people usually talk about finitary monads on set, it turns out that for today's purposes, it's going to be more helpful to think of them as strongly finitary monads on set. Now this relationship is very useful because it gives us three different ways to view algebraic structure. We've got the traditional classical way of reasoning syntactically using equational logic. We've got the first categorical formulation due to Levier represented using algebraic theories. And then we've got the monadic viewpoint, sort of more categorical algebraic perspective. And these are complementary, and there are some theorems that are easier to prove using one perspective than the other. So it's helpful to have all three of these. Now I'm going to introduce second-order algebraic theories, which are an extension of first-order algebraic theories, i.e. normal algebraic theories introduced by Marcello Fiori and Ola Mahmoud in 2010. So motivation behind second-order algebraic theories is there are some structures which seem essentially algebraic, by which I mean they look almost algebraic, but their operators don't quite fit the normal structure that we'd expect. So they don't fit into the algebraic theory framework. So here are some examples of second-order operators. And the intuition here is that second-order operators are those that bind variables. So anytime you see an operator which quantifies over some variable x, for instance, there's a good chance this is a second-order operator. So a classic example from mathematics, calculus, are differential operators. So here at the top, you view f as being a function because f has a free variable x in it. And we also have a point x naught that we will evaluate derivative at. So our operator df by dx at x naught is the derivative of f evaluated at x naught. Secondly, we have logical quantifiers like existential and universal quantification. These are also second order operators. And possibly the motivating example is the lambda abstraction operator from the simply type lambda calculus or unitype lambda calculus, which is the classic notion of variable binding operator in type theory. And this is sort of the motivation for thinking about second order operators in the first place. Here are a couple more examples with sorts. So at the top, we have case splitting operation in if we want to talk about coproducts, for instance, in a type theory with sum types. And we also have fixed point operators. So there's one other class of examples I just briefly want to mention, which are the parameterized algebraic theories that were introduced by Sam Staton in 2013. A parameterized algebraic theory is intuitively a way to capture a family of algebraic theories that are related in some way by parameterization. And if you check out Sam's papers, he gives several nice examples, and it turns out that every parameterized algebraic theory is a second order algebraic theory in the sense I'm about to introduce. So as in a first order algebraic theory, where we have a base category representing the structural operations and another category giving the term structure of the theory, we would like to figure out what the appropriate structure is to represent the second order operators. So I'm going to introduce this category on the left, which we call the second order theory of equality. And I'm going to denote this L2. So before we took the free Cartesian category on a single generating object. And now we're going to take the free Cartesian category on an exponential object. So this is one where we can raise any other object to the power of this object. So the right adjoint of taking the product of this object exists. Concretely, the objects of this category are going to be given by products of these exponentials and the morphisms given by the universal property. Now, the important thing to take in here is that the objects of this category are parameterized by the objects of the original base category, the free Cartesian category on a point. And this will be a common pattern throughout the talk, that the nth order algebraic theories are going to parameterize the n+1th order algebraic theories. And we start to see this pattern occurring here. And so the idea will be that our objects represent sort of higher order structure in that they're taking inputs from the previous level of theory. So once again, we can define a notion of algebraic theory, in this case, a second order algebraic theory. And now our structure is going to be Cartesian categories, categories with finite products with a single exponential object. And then we're going to take these identical objects, Cartesian functors, which reserve the exponential object. Now, how can we think about these syntactically to get some intuition for how these represent the second order structure? Well, if we consider a morphism as before, again, a morphism represents a tuple of terms given by the universal property. But now, instead of just being terms in a number of variables, we're also going to parameterize a number of metavariables. And a metavariable is intuitively a parameterized variable. So it's a variable that has a value when evaluated, having been given certain inputs. So on the bottom left here, I've written an example of a parameterized variable. So x1 is going to take inputs x1, 1 through to x1, n1, and so on. And we can also parameterize by ordinary variables as before, though these are equivalent to nullary metavariables, so metavariables that don't parameterize over any variables. And yeah, I'm going to give you an example to give some intuition, but one way to think about these parameterized variables is that the variables have type of a function type. So the variables themselves take inputs. So if we want to represent a differential operator like before, so here we want to differentiate f of x with respect to x and then evaluate at x0. This is going to be represented by a morphism from x dx, representing the binding of x in f of x, times x, which represents our x0, to x. Now, once again, we can talk about the category of algebraic theories, and the morphisms are just as before, they're just these commutative triangles. And second order algebraic theories with their maps form a category which I'm going to call law 2 for second order algebraic theory. Now, from before, we have some natural questions to ask about this category. For instance, we'd like to know whether it has limits, colimits, perhaps some universal property. We're particularly interested in limits and colimits, again, because we'd like to be able to combine things like presentations of second-order algebraic theories. And this would allow us to, this would be useful, especially in things like programming language theory, where you might want to take a second-order algebraic theory representing a simple programming language and extend it by an effect or a new operator.
Can I ask one question, actually?
Yeah, please
so
do.
When you say you would like to know, does law 2 have a universal property? So like, if law 2 is a generalization of law 1, does law 1 have a universal property that maybe motivate or?
Yeah, I was a bit vague here. By universal property, I was really referring to the fact that law 1 is the sifted co-completion of a particular small co-Cartesian category. And so in a sense that characterizes it fully.
Okay.
So that's the sort of thing I mean by this. Yeah, I was a bit vague.
Great. I wasn't sure.
Yeah, so perhaps more interestingly, again, we'd like to know whether we can again reason about this second order algebraic structure using some form of monad. Because as we know, the monadic perspective is very useful for ordinary algebra. And so we imagine it would also be very useful for second order algebra. So these are sort of the motivating questions for this research. But before I get into those, I quickly want to talk about higher order algebraic theories. It turns out that the structure that I'm going to talk about is naturally based on the relationship between nth order and n+1th order algebraic theories. And so it helps to abstract away from 1 and 2. Now, there's a natural question to ask here, which is, are there any natural examples of third order or higher operators? And the answer is that it's a lot harder to find examples of third order operators and higher. I do have 2 examples. So in programming language theory, we care about things called continuations. I'm not going to go into detail about what these are, but if you've heard of them, then you'll know what I mean. Things like the cool CC operator. And we also have selection operators, which again are used in programming language theory, but also in mathematics as well. And so these are 2 examples of third order operators. I don't have any natural examples of fourth or higher order operators. So it really does get more sparse here, but it's helpful anyway to think about nth order for arbitrary n to sort of abstract away from the necessary details. So again, we want to have this sort of structure where we have a category providing the structural operations of the theory and another category giving the terms and equations. So in this case, the appropriate base category is a category we call Ln. So before we took the free Cartesian category on an exponential object, and now we're going to take it on an n-tetrable object. And this is an appropriate higher order generalization of exponentiation where we ask for the generating object x to be exponentiable a fixed number of times. So in the first order case, x is not exponentiable at all. In a second order case, we are able to exponentiate x by itself once. And in the third order case, we're going to allow x to the x to be exponentiated as well. So intuitively, the morphisms in this category are going to represent operators that themselves take operators as their operands. And this may continue depending on how n is. So the operators that are taken as operands may themselves take operators and so on. And I guess there's a familiar intuition from Cartesian closed categories, especially in categorical logic and semantics. So one thing to note is that these free Cartesian categories on n-tetrable objects include into the next one along in this chain. And this gives us sort of a spectrum from the free Cartesian category point to the free Cartesian closed category point. So whenever I say n in this talk, n refers to the extended natural numbers, so natural numbers with omega as well, representing unlimited, unbounded orders to the operations. And now that we've established what the base category is, the structure of the algebraic theories are clear, we're going to look at Cartesian categories with these n tetrable objects and identity and objects functors preserving all that structure. So the finite product structure and this exponential structure. And the map of nth order algebraic theories is just a commutative triangle as before. Just a note that whenever I say higher order algebraic theory, it's just an nth order algebraic theory for some n. So again, these form a category, which I'll call law n.
Maybe I can ask you one more question, because there's
sure.
a question in the chat, which is, why is L omega the free Cartesian closed category?
The idea is that when every object is exponentiable, then every object is exponentiating, I think is the adjective. So it turns out that when you can exponentiate when a single object can be exponentiated an arbitrary number of times, all of your objects can be exponentiated an arbitrary number of times. This turns out to have the right property. I guess the easiest way to see this is, for me, is a syntactic argument based on the simply type round calculus. Yes. So again, we have these questions from before that we also want to ask for law n. So we want to know how well behaved it is in terms of limits, co-limits, whether we can describe to some sort of co-completion, for instance, and also whether there's a monad correspondence for these nth order algebraic theories. So to answer the first question, I'm going to introduce the notion of exponential subcategory. So we're going to say a subcategory is exponentiable if for all of the objects in the subcategory, the object is exponentiable in the supercategory. So the product, the functor given by taking products has a right adjoint. And the sort of motivating example for this concept is the inclusion of Ln into Ln plus 1. This is an exponential subcategory. So we're going to denote by exp(n) the category whose objects are these chains of exponential subcategories of length n, and whose morphisms are functors making the squares commute, and also preserving the exponential objects where appropriate. I just want to note that whenever I say exponential subcategory, I'm talking about Cartesian categories. So all the categories here assume to have finite products, and the functors are preserving the finite product structure. Now we have an adjunction between the two consecutive levels between the chains of length n and the chains of length n plus 1. And it's the left adjoint here that we're particularly interested in, which is given by freely adding a layer of exponentials to Cn, to the last object in the chain. So this is a restriction of the Cartesian closure, the Cartesian closed closure of the last object, where we want to preserve the exponentials that already exist, and we just want to add one level of them. And the right adjoint is just going to be given by forgetting the last category in the chain. Now, the important construction here is this conservative Cartesian closed closure, which I'm denoting by C tilde. And the reason we're interested in this construction is that we have this proposition. So if C1 to C2 is an exponential subcategory, then the strict Cartesian functors from C2 tilde, so this conservative addition of exponential objects, intersect, are in bijection with the strict Cartesian identity on objects functors out of C2, so out of the supercategory, that preserve the exponentials from C1. This is a bit of a mouthful, but I'll explain why this is interesting in a moment. And the idea behind this intuition is that if we take such a Cartesian functor, then we can look at the action on the freely added exponentials, and these give a set which we take to define our Hom sets for the category and the codomain of our identity on objects functors. And because exponentiation has a sort of internal composition operation, this internal composition induces the composition in the category we're defining. Now, as before, I said the motivating example of these exponential subcategories is the inclusion of Ln to Ln plus 1. And so we're going to substitute this exponential subcategory into this previous proposition. And I've just substituted the various occurrences in blue here. And so if we just look at the statement, it says that Cartesian functors out of Ln plus 1 tilde, which turns out to be the same as Ln plus 2, because we're freely adding a layer of exponentials, which is what going from Ln plus 1 to going from Ln plus 1 to Ln plus 2 is doing. These functors are in bijection with these commutative squares where the horizontal morphisms are identity on objects functors. And it turns out that these are exactly n plus 1th order algebraic theories. And to summarize, to make it a bit clearer, because that was quite a long-winded statement, this says that the category of nth order algebraic theories is given by taking Cartesian functors from Ln plus 1, so the initial object from the next level of algebraic theories. And because Ln plus 1 is a Cartesian category and it's small, this means that law n is the sifted co-completion of the free Cartesian category in an n plus 1 tetrable object. If we substitute n equals 1 for this, we get the statement we already knew, but possibly didn't have an explicit characterization for, which is that law 1 is given by the sifted co-completion of L2 op, where L2 is a free Cartesian category on an exponential object. And we get various nice corollaries of this result. For instance, it's locally finite presentable, and it's co-complete and complete, which answers the other question we had about colimits and limits. Now, I just want to mention—
Nathaniel,
yeah.
Can I ask just one question?
Yeah.
But now, so functors are preserving everything on the nose, because so inside law n, you are forgetting any two-dimensional structure, and even the notion of functor must preserve the structure on the nose, not up to ISO. Okay.
Yeah. Yeah. So
and is this natural or not? Because for me, law has a two-dimensional structure.
So I think this depends on what you're motivated by. So traditionally, the category of algebraic theories as identity on objects functors is a one category. And this is because the two-dimensional structure is sort of trivial in some sense, because you're taking identity on objects and strictly Cartesian functors everywhere. However, often when people talk about algebraic theories, they're meaning Cartesian categories, in which case you do have a natural two-dimensional structure. I guess the moral here is that either one works. We're taking very strict structure because we're interested primarily in the identity on objects functors with strict preservation everywhere. You can weaken it and it works as well. So it really just depends on what your motivations are.
Maybe a comment, just in cat, every bijective in objects functor is a discrete iso cofibration, which means that you can uniquely extend natural isomorphisms along it, so you can turn, so that sort of means you can eliminate natural isomorphisms and things like that, and get rid of the two-dimensional structure and work with it as strictly as possible without actually losing anything.
Thanks, that's a helpful comment. I wanted to mention one thing quickly here, which is a paper by Taichi Umura from last year. And I think Taichi gave a talk at this seminar a little while ago, and he presented a result which looks quite similar to this one, but for the finite limits case rather than the finite product case. So the result in this paper is that the category of generalized algebraic theories, which is sort of a dependently typed analog of the category of algebraic theories, is the incompletion of the free finitely complete category on an exponential morphism. And so this sounds very similar, and I guess this is the simply typed, well, at least when n equals 1, this is the simply typed version of Umura's result. Now we get some other nice corollaries of this characterization, which is that we have a co-reflection of categories from law n into law n plus 1. And intuitively, the left adjoint here is treating a presentation of an nth order algebraic theory as a presentation of an n plus 1th order algebraic theory with no higher order operations, so sort of a more trivial n plus 1th order algebraic theory. And the right adjoint is going to discard all the n plus 1th order terms. So if we, in terms of presentations, if we generate all the terms from the operators in our n plus 1th order theory, and we just remember the nth order terms, we get an nth order algebraic theory, and this is the right adjoint. And abstractly, the way to see this is that if we take the representations of these nth order algebraic theories as sifted co-completions, we have this inclusion from Ln plus 1 into Ln plus 2. And this induces an algebraic functor, which is this right adjoint. And algebraic functors have left adjoints, which is exactly this left adjoint here. And so it follows from the theory of algebraic theories, algebraic categories. And what's more, we have this chain of co-reflections, including a co-reflection into law omega. And this allows us to freely extend or restrict an nth order algebraic theory to any other order by either trivially extending it and having no higher order operations, or forgetting all the higher order terms that are induced by the theory. Okay, now I want to talk about the main result, sort of the core motivation for the work. And you may notice that at the start, I asked, well, we'd like to know whether there is a monad correspondence to these higher order algebraic theories. And the title of the talk and this slide is called Relative Monads. And the reason is that it turns out to be more convenient to consider relative monads first. And from there, we can deduce a monad correspondence. So what are relative monads? They're maybe a slightly uncommon structure. So I'm going to introduce them as well as relative adjunctions. So don't worry if you haven't come across them before. So a relative adjunction is like an adjunction, but relative to some functor. So intuitively, we have a triangle like this where L and R now no longer have the same domain and codomain. They've sort of been extended along J. And so if you look at the Hom set definition of a relative adjunction, you'll see it's very similar to the definition of an adjunction. But the difference is that on the right here, we're including X into C via J. And this generalizes the notion of adjunction, because when we take J to be the identity, we get back the notion of adjunction. One thing to note is that the notion of relative adjunction is not symmetric. You have left relative adjunctions and right relative adjunctions. depending on whether J is on the left or the right. But if we care about relative monads, then this is the form of relative junction we care about. So just as there's a tight correspondence between adjunctions and monads, traditionally, there is also a tight correspondence between relative junctions and relative monads, as one might hope. So I've written down the structure of a relative monad here, but actually we're not going to worry about them too much because for our purposes, it won't be necessary to know what a relative monad is, just that they exist. Possibly the important thing to note is that a monad is precisely an identity relative monad, so a monad for which we're taking this J here to be the identity functor, as we might hope. And the other key fact is that every relative adjunction induces a relative monad. And conversely, every relative monad is induced by two relative adjunctions, the Kleisli construction for relative monads and the Eilenberg-Moore construction for relative monads. So at least in CAT, relative monads work very nicely, very similarly to monads. So we can use that intuition here. There's one more construction I have to introduce, which is a construction that's familiar from categorical logic, categorical semantics. It's called the simple slice category. And this comes up in, say, the theory of the simply typed lambda calculus and Cartesian closed categories. So we're going to define the simple slice category over a category L and an object X in L to be a new category with the same objects, but whose Hom sets are defined by extending the domain of each morphism by X. So from a syntactic perspective, we're extending the context of each term by a new variable of type X. And possibly the intuition here is that the simple slice category has a universal property, and it's the result of freely extending this category L by a single morphism from the terminal object into X. And this gives us back this intuition of extending context by a new variable. So now we can talk about how to go between theories and relative monads. So let's say that L is an n+1th order algebraic theory. So it's this identity objects functor from Ln+1 into some Cartesian category with this tetrable object. Now there's a relative adjunction given by this triangle. So here I'm using Yo to stand for essentially the Yeneder embedding, but for the SIND completion. So it's the inclusion of Ln+1 op into its sifted co-completion. And on the left, the relative left adjoint here is the opposite of our n+1th order algebraic theory. And our right adjoint is given by taking the slice construction that we saw before, and then forgetting all the higher order operations. So going from n+1 order operations to n order operations. And it turns out that this induces a relative adjunction. And this is essentially following all the universal properties I've described before. And since we have a relative adjunction, we can compose the left adjoint and the right adjoint, and we get a relative monad. So given any n+1th order algebraic theory, we have a relative monad. Now let's look at the other direction. So given a relative monad along this functor on the bottom, along the inclusion into the sifted co-completion, we have a relative adjunction given by the Kleisli construction, just as in the normal monad case. Now, a Kleisli inclusion is an identity objects functor, and it also preserves coproducts very easily. And so we almost have what we're looking for, because if we take the opposite of this inclusion, we have an identity objects functor that preserves finite products. However, in general, this functor isn't going to preserve exponentials, which is a problem. So we're going to have a brief interlude to talk about when a Kleist inclusion preserves coexponentials. And I'm saying coexponentials because we want the opposite of the inclusion to preserve exponentials. So we have to dualize here. Now you can just write out what you need for this to work and observe what goes wrong when you are looking for this preservation of coexponentials. And it turns out it's this step in the middle. And this means that for the Kleist inclusion to preserve coexponentials, we need this isomorphism on the right to hold. And I've just written isomorphism, but really it's a canonical isomorphism. So we want the canonical strength for the coproduct to be invertible here. And we're going to call these relative monads plus linear. They're called plus linear because there's a notion of linear monads where you have an invertible strength, and these correspond to a certain class of enriched monads, and that's where the name comes from. What the thing to note here is that plus linearity is trivial when n equals 1, and this is why we don't see this condition appearing for first-order algebraic theories. The way to see that's trivial is because in a first-order algebraic theory, we have no exponentials, and so we don't need to preserve any for the monads. Now, this is the triangle we had before, and we're going to adjust it slightly. We're going to add this one extra condition, this plus linearity condition, which means that the strength for the coproduct is invertible. And now if we try doing what we did before, it turns out that everything works. The inclusion of the inclusion into the Kleist category, if we take its opposite, is an n+1th order algebraic theory. And it turns out this defines an equivalence, well, even an isomorphism of categories. The morphisms are no problem to include in this bijection between n+1th order algebraic theories and plus linear relative monads along this inclusion of ln+1 into law n. I'm going to give a bit more intuition for what this means in a moment, so don't worry if this looks very strange. But first, I quickly want to mention what happens with ordinary monads, non-relative monads. Well, there's a very useful general theorem we can apply here. When C is a locally strongly finitely representable category, then we have an equivalence of categories between relative monads along the inclusion of the strongly finitely representable objects in C, into C, and the category of strongly finitary or sifted co-continuous monads on C, i.e. the SIND completion of the category of strongly finitely representable objects. And so this extends to incorporate the plus linearity condition. And so we get that law n is also equivalent to the category of plus linear strongly finitary monads on the category of nth order algebraic theories. And this is possibly the slightly more convenient way to think about these n+1th order algebraic theories. They're given by taking some construction, i.e. sifted co-continuous monads, satisfying some condition, on the category of nth order algebraic theories. And to give slightly more intuition for this construction, we can explicitly describe what these monads look like. So if we take an n+1th order algebraic theory, then the corresponding monad is given by taking an object x, so x here is an nth order algebraic theory. Then we're going to consider x as an n+1th order theory, one with only trivial higher order operations. We're going to take its coproduct with the n+1th order algebraic theory that induced the monad, and then we're going to forget all the higher order operations. And so if we look at the n=0 case, so the traditional first order setting, this says that the monad induced by an algebraic theory or a Levier theory takes a set of constants and it freely adds them as constant operators to L. Then it closes these operators under the operations of L and then extracts the new constants that are generated. So all the terms in empty contexts. Yeah, I'm going to give slightly more justification for why X is a set here in just a moment when n equals 0. But that's the intuition. So just as in the first order case where we have a Cohen formula for the monad, we also have a Cohen formula for the monads for arbitrary order algebraic theories. Just going by this. Now, I think I have 5 more minutes, so I want to very quickly mention algebras and also very quickly mention 0th order algebraic theories. So in the classic setting, the models of an algebraic theory, let me rephrase that. If you take an algebraic theory, take its induced monad, then the algebras for the induced monad coincide with the models for the original theory. And we have something very similar in the higher order setting. In fact, it looks exactly the same as before. So if we have an n+1th order algebraic theory, and we take the corresponding monad on law n, then the algebras for the monad are equivalent to the Cartesian functors from L into set. Now there's one detail here which might be slightly surprising, in that even though we're talking about higher order structure, which naturally has exponential structure, the algebras for the monad are equivalent to the Cartesian functors just preserving the products and not preserving the exponentials. And it turns out there's an interesting divergence between the notion of algebra and what might naturally be considered a notion of model in the higher order setting, where the models should preserve exponential structure, but the algebras should not. And this is quite interesting, but something I don't have time to get into, so will be discussed more in the corresponding paper. Now, very quickly in the last few minutes, I want to talk about the notion of a 0th order algebraic theory. So I think this is quite a nice way to tie everything together. So it's well known that in the classical setting, algebraic theories correspond to strongly finitary monads on set. And since we have this formula from before that tells us that n+1th order algebraic theories are given by taking monads on the category of nth order algebraic theories, and we know that this linearity condition is trivial when we don't have any exponentials, then we might be led to conclude that the category of 0th order algebraic theories should be the category of sets. And we could just define it this way, but it would be nice if there was an intuitive way to see why this was the case. So we're going to define a 0th order algebraic theory to be a strict terminal object preserving identical objects functor from L0, where L0 is the free category with a single object and a single object adjoined by a terminal object. So we have a single object X. We've got 2 objects, X and 1, and a single morphism. So this is the interval category. And we're also going to ask, which is something that we don't need to do in the first and higher order setting, that every morphism in L is constant, so it factors through the terminal object. This may seem a little bit of a weird definition, but we can rephrase it that makes it sound a bit more natural. So we can define these 0th order algebraic theories as generalized operads for the terminal monad. And so maybe this makes them seem slightly more natural. It's very easy to see that the 0th order algebraic theories are essentially the same as sets, because we can just look at the morphisms from the terminal object into the generating object X, and this gives us a set. And that's all the information that is present in the category. And so this gives us an isomorphism between 0th order algebraic theories and sets. But notice now that the 0th order algebraic theories are defined as identical objects functors, so they feel a little more like the algebraic theories that we're used to. And essentially everything works for the n = 0 case, just as it works for everything else. So recall that law n is given by the sifted co-completion of law n+1 op. Well, if we substitute n = 0 here, we get that law 0 is the sifted co-completion of L1 op, and L1 is the free Cartesian category. L1 op is the free co-Cartesian category, which is equivalent to the category of finite sets and all functions between them. And the sifted co-completion of the category of finite sets is just the category of sets. And so everything works out as we expect it if we take this to be our definition of zeroth order algebraic theory. And as a final corollary, we get that the category of nth order algebraic theories can be expressed inductively by iterating this construction of taking the strongly finitary plus linear monads on starting from law 0. And this is quite a nice inductive formula for the category. The one final thing I want to mention is that throughout this talk, I've just been considering one-sorted algebraic theories, but everything that I've said today works for S-sorted for some set of sorts. The theory is essentially exactly the same, and this formula holds where we take law 0, the S-sorted algebraic theories, zeroth order algebraic theories, to be S-index sets, and everything continues to work as before. So with that, I'm going to end. And just to summarize what I've mentioned today, we have this notion of higher order algebraic theory that generalizes algebraic theories by adding these higher order variable binding operators. We have these co-reflections between the different categories of nth order algebraic theories that allows us to move between different orders. We have this characterization of the category of nth order algebraic theories as a sifted co-completion, and also as a category of monads on the category of algebraic theories from the order below. And finally, there's a natural way to see that sets are the correct notion of zeroth order algebraic theory, which sort of ties everything together. So any construction you see about algebraic theories, which involves sets, it's likely when you generalize it to higher order algebraic theories that this, instead of being construction on sets, is construction on the algebraic theories from an order below. So yeah, that's it. And I'll be happy to take any questions.
All right, let's thank Nathanael for a great talk, very interesting. We have our usual silent round of applause. So if you have a question, go ahead and ask. Feel free.
If I may ask a question. Nathanael, beautiful talk, I loved it. I would like to ask something about semantics. What about the models? What do you know, and what kind of usual structures of mathematics we can discuss? For example, is the category of models, how bad is the category of models of such a theory? I asked you once if I can axiomatize top, and you told me I can't. What else can I do?
So this is one of the questions that gets into this interesting, surprise perhaps, that the category of algebras for the corresponding monads are Cartesian functors. And so if we take the notion of model of a higher order algebraic theory to be a Cartesian functor, which is what's suggested by the monad correspondence, then we can capture with higher order algebraic theories the same things we can capture with algebraic theories, because as long as we're happy to go to multi-sorted algebraic theories, because we can just take L to be some Cartesian category and forget that has any exponential structure. So in that sense, the algebras are not any more interesting from things we're able to capture. So what we really want to do is consider models. And so models are going to be some notion of essentially Cartesian closed functor, but just preserving the exponential structure we have. And the awkward thing with this notion of models is there's no good notion of two-cell. So no notion of morphism between models. And this is a well-known problem. It's the reason that the free Cartesian closed category construction is not a two monad on cat. It's only a one monad, because unless we take natural isomorphisms rather than natural transformations. So the problem is this contravariance. And so it really only seems reasonable to consider models in other higher order algebraic theories, or models if we don't care about the morphisms. And so this means that asking what categories of models looks like is a little bit of an awkward question to ask, because the notion of morphism seems not so well behaved. So a better question maybe is what structures we can capture if we don't worry about the morphisms between them. And then there are quite a lot of examples from computer science. Well, because anything involving variable binding operators like reflexive objects, which interpret the structure of the untyped lambda calculus, for instance, is an example of a model of a higher order algebraic theory. Yeah, but when it comes to the category of models, I'm not sure there's so much we can say that's interesting beyond the first order case.
Thank you.
Any more questions? You mentioned connections with Tai Chi, Umura's work, which is where you have some exponential morphisms rather than objects.
Yeah.
Can you view these kinds of theories as theories in that setting, or can you?
This is something I'd like to know. So maybe there are two things I can say here. One is that I guess one of the motivations for this work is the monad correspondence. And so you get this very nice relationship between algebraic theories of order n+1 and monads on algebraic theories of order n. And because there's not a monad correspondence per se for essentially algebraic theories, it seems unlikely this correspondence works in just the same way there, although there is a relationship between, I think we're called essentially monadic chains or something like this, and essentially algebraic theories. And maybe this theory could be used to give a similar result. The other observation is that I guess my comment is that I'd very much like to see how much of this theory would work defining higher order essentially algebraic theories using similar ideas. The one difficulty I see at the moment is that I think you essentially need to cater that theory. You need to read all the theory. I'm not sure what the general development would be that would specialize to give both the algebraic theory setting and the essentially algebraic theory setting. So I have no idea how much of this would work in that setting. It'd be interesting to think about. It's a good question.
Yeah, okay, thanks. Yeah, I have a silly idea and picture in my head of a square where you have, Levier theories and then finite limit theories, which is quite a lot bigger. And then you have your higher order algebraic theories sitting over the Levier theories, and then this stuff of Tai Chi up in the other corner. But of course, there's quite a big difference between Levier theories and finite limit theories, and there's lots of things you can say about Levier theories like monadicity and stuff, or connections there that just aren't maybe relevant, or
yeah.
So, but I don't know.
My feeling is that there ought to be some sort of relationship like that, and it should generalize to arbitrary orders as well, giving you locally Cartesian closed categories at the top. But yeah, one would need to check.
Okay. Any more comments or questions? Well, if not, then let's thank Nathanael again for a great talk. So thanks very much for that, Nathanael. That was really good. And so next week we have Tashi Balda will be giving a talk, though I don't have the title yet. But so that's it for today. So we can stop recording.